to this quick introduction to the Cifar-100 dataset, a benchmark dataset in machine learning and computer vision research. Before we dive into the details, here's a quick roadmap of what we'll cover. First, we'll look at the dataset overview and basic statistics. Next, we'll explore its application in machine learning models. Then, we'll dive into the Vision Transformer, or ViT, with a focus on its performance using the Cifar-100 dataset. Finally, we'll wrap up with the conclusion. Let's get started. What does Cifar-100 contains? Is a subset of the Tiny Images dataset and consists of 60,000 32 by 32 pixel color images. The 100 classes in the Cifar-100 are grouped into 20 superclasses. There are 600 images per class. Each image comes with a fine label, the class to which it belongs, and a coarse label, the superclass to which it belongs. There are 500 training images and 100 testing images per class. How are they labeled? Coarse label is a broad or general category that groups similar items or concepts together. For example, animal is a coarse label, and fine label is a more specific or detailed category within a broader coarse label. For example, within the coarse label animal, fine labels could include dog, cat, or elephant. Here's an example. The mammals group, coarse label, includes bear, fox, and tiger. The vehicles group includes bicycle, train, and pickup truck. The dataset is divided into 5 training batches and 1 test batch, each with 10,000 images. The test batch contains exactly 1,000 randomly selected images from each class. The training batches contain the remaining images in random order, but some training batches may contain more images from one class than another. Between them, the training batches contain exactly 5,000 images from each class. Each fine category has 500 training images, almost 83.3% of the total, and 100 testing images are 16.7%. This is considered a good balanced distribution for fairness and accuracy in model training and evaluation. Now, we're diving into the next milestone of our video, which is Cifar-100, application in machine learning models. We will cover aspects like challenges and the typical usage of this dataset. The Cifar-100, used in general as a benchmark dataset for testing and improving scalable multi-class classification models. Researchers use it to explore areas like 1. Neural Architecture Search, NAS. 2. Understanding feature representation in deep learning models. 3. Testing generalization in low-resolution vision tasks. In this section, we'll explore these applications one by one. Let's dive right in. First up, Cifar-100 plays a critical role in neural architecture search. Think of it as a way to explore various architectures to find the most effective one for a specific task. Speaking of neural architecture search, a paper titled Efficient Evolutionary Neural Architecture Search, based on hybrid search space, demonstrates how Cifar-100 serves as a powerful tool for designing and optimizing neural networks. This paper suggested the best neural network design for Cifar-100, which will be used later for other multi-class classification problems. One great example is efficient net architecture, a model that found the right balance between accuracy and computational cost. It was tested on Cifar-100 first, proving its scalability to bigger datasets. But there are a few challenges. Limited data per class. While Cifar-100 has 60,000 images, these are evenly distributed among 100 classes, meaning only 600 images per class. Class imbalance sensitivity. Although Cifar-100 is balanced in terms of the number of samples per class, the real-world relevance of these classes might vary. Secondly, let's talk about feature representation. Basically, how deep learning models see and understand images. Cifar-100 helps researchers to study how early layer detects things like edges and textures, while deeper layers capture more meaningful patterns, like recognizing objects. It's also a go-to dataset for interpreting activation maps, which are like heat maps showing where the model is focusing. But this isn't easy. Fine-grained categories, like different types of flowers, can confuse models due to their high similarity. The dataset's 32 by 32 resolution means some critical details are lost, which can lower the performance. And sometimes, models pick up biased patterns, making them less reliable in real-world settings. Finally, generalization, which means how well a model performs on new, unseen data. Still, there are challenges here too. Challenges like low resolution, limited context, and fine-grained classes can make it hard for models to generalize. Now, we're diving into the last milestone of our video, where we'll be speaking about vision transformers, or ViTs. This dataset is ideal for testing ViT capabilities because of two main reasons: multi-class complexity. The dataset's diverse classes challenge the model's ability to distinguish fine-grained categories. Low resolution. The small image size tests how well ViTs can handle datasets where high-resolution details are absent. Let's take a closer look at how vision transformers process Cifar-100 data, step by step. Step 1. Pre-processing. Cifar-100 images are divided into patches, such as 4 by 4 or 8 by 8, depending on the ViT's architecture. Each patch is flattened and passed through a linear layer to create embeddings, which are enriched with positional encodings to preserve spatial relationships. Step 2. Transformer pipeline. The embedded patches form a sequence and are processed through multiple transformer layers. Here, multi-head self-attention learns global relationships between patches, and feed-forward layers further refine these representations. Step 3. Classification. A class token is added to the sequence. Its representation, after passing through the transformer layers, is used for final classification. This global token summarizes the image features into a single output vector for the classification head. Now, let's discuss the key findings when applying vision transformers to Cifar-100. 1. Attention. Visualization attention maps reveal how ViTs focus on specific parts of the image. For Cifar-100, ViTs effectively prioritize relevant regions, even in visually complex classes. 2. Fine-grained feature learning. While CNNs often struggle with similar classes, like pine tree versus oak tree, ViTs show improved differentiation by considering broader relationships across the image. 3. Generalization. ViTs fine-tuned on Cifar-100 can generalize to other datasets with similar resolutions or image compositions, making them versatile for transfer learning. But there are some challenges when applying ViTs to Cifar-100. 1. Low resolution. The 32 by 32 size limits the amount of detailed information available, leading to potential underperformance compared to higher resolution datasets. 2. Limited data per class. With only 600 images per class, overfitting becomes a risk. Data augmentation techniques like random cropping and flipping are crucial. 3. Computational cost. Despite the dataset's small size, the transformer-based architecture can be resource-intensive during training. Finally, we reach our video conclusion. Machine learning and vision transformers. ViTs offer unique but complementary strengths in image classification tasks, especially when applied to datasets like Cifar-100. Traditional machine learning models, such as CNNs, excel in capturing local patterns like edges and textures, making them efficient for low-resolution images. In contrast, ViTs leverage self-attention mechanisms to capture global relationships, enabling them to distinguish complex, fine-grained features across multiple classes. While ViTs are computationally demanding, they bring superior generalization and scalability to larger tasks. That's all for our video today. We hope you enjoyed these 10 minutes. See you again soon. Bye-bye.